This is my first example of the law of conservation of momentum at work. Let's jump right in. At the bowling alley, a player rolls a 5.4 kilogram bowling ball with a speed of 6 meters per second towards the pin, whose mass is 1.5 kilograms, and it's at rest at the end of the lane. And after the collision, the pin bounces away from the bowling ball with a speed of 12.7 meters per second. And we're being asked here, determine the speed of the bowling ball after its collision with the pin. So let's start by drawing a picture of the situation, okay? So we've got, I'm gonna first divide this up into my before and my after. Okay, so before we've got this bowling ball, it's moving down the bowling lane towards a bowling pin. The mass of the bowling ball is 5.4 kilograms. The mass of the pin is 1.5 kilograms. I'll call the bowling ball mass 1. I'll call the pin mass 2. And then we have these velocities as well, right? So I'll call this V1 initial is 6 meters per second. And then the bowling pin's initial velocity, call that V2 initial, is 0. It's at rest. Okay? So here's our bowling ball moving towards our bowling pin. All right, after the collision, the bowling ball knocks the bowling pin away. Okay, so now the bowling ball's at the end of the lane. It's moving this way. And it knocks the pin over, right, with some velocity. Okay, so we're told that the velocity of the pin, we're going to call this V2 final, is 12.7 meters per second. And it says determine the speed of the bowling ball after its collision with the pin. So we're being asked to find V1 final. What is the speed of this bowling ball after the collision? Okay, so first, if we want to solve this problem, we need to identify the type of collision, okay? And in this case, since the bowling ball is hitting the pin and the pin is bouncing, right, here's the key word, it's bouncing, then this must be an elastic collision. So let's start with the conservation of momentum equation for an elastic collision. It goes like this, right? M1 V1 initial plus M2 V2 initial is going to be equal to M1 V1 final plus M2 V2 final. Okay, what that's saying is the total momentum of the bowling ball and the pin before the collision is going to be equal to the total momentum of the bowling ball and the pin after the collision, okay? This is the bowling ball, object 1. This is the pin before. This is the bowling ball after the collision, and this is the pin after the collision, okay? Total momentum is supposed to remain constant. That's what it means to say that momentum is conserved. All right, so let's plug in our numbers, and we're going to solve for V1F, right? This one is going to be our unknown. That's what we're going to do the algebra to solve. So here we go. The mass of the bowling ball is 5.4 kilograms. Its initial velocity is 6 meters per second. We're going to add that to the mass of the bowling pin, 1.5 kilograms, an initial velocity of 0. So that's just going to go away. And then we're going to set that equal to the momentum of the bowling ball, which is 5 kilograms times its final velocity, plus the momentum of the pin, 1.5 kilograms times its final velocity of 12.7 meters per second. Okay, so on the left side, we get 32.4 kilogram meters per second of momentum. On the right side, we're going to get, and my mistake, I think I made a copy error here. This is 5.4 kilograms. So 5.4 kilograms times the final velocity of the bowling ball plus the momentum of the pin after the collision, which is going to be 19.05 kilogram meters per second. Okay, so bringing this over to the other side, right, subtracting both sides by 19.05, I get 13.35 kilogram meters per second is going to be equal to 5.4 kilograms times the final velocity of the bowling ball, which means the bowling ball's final velocity is going to be 2.47 meters per second. And then I would want to ask myself, does that make sense? Does that make sense? Okay. Well, look at the bowling ball's initial velocity. It was 6 meters per second. Okay. So if it collides with the pin, would I expect it to go faster or slower after the collision? I would definitely expect it to go slower, right? Here I'm showing that the velocity is going to drop to 2.47 meters per second. And one reason why I would expect it to go slower is because it's transferring some of its momentum to the bowling pin, right? Look at what's happening to the bowling pin. The bowling pin starts at 0 meters per second at rest, and then after the collision, the pin increases its velocity to 12.7 meters per second. So the pin in this example is gaining momentum, the ball is losing momentum.